Hello friends, welcome back to my YouTube channel. In this video, I'll be continuing my discussion on distillation. This would be 34th part of that discussion, and today I will be discussing a numerical that is based on McCabe Thiele method. Actually, this will be third numerical based on the McCabe Thiele method. In my earlier videos on the McCabe Thiele method, I have discussed two numericals. So in that way, I'm calling this as the third numerical. I have discussed the McCabe Thiele method in details. The important aspects of the McCabe Thiele method I have discussed in my earlier videos on the topic. I am giving links to related videos in the description section of this video. So today we will be discussing a numerical where you learn how to calculate the minimum reflux ratio that can be used in a typical tray column, and then you'll also learn to find the minimum number of stages that can be used when the column is operating under a total reflux. Okay, to begin with, let us first look at the numerical statement. The feed to a fractionating column is a saturated solution of heptane and ethyl benzene. It contains 42 mole percent heptane and rest is ethyl benzene. It is admitted at a rate of 630 kilomole per hour. The objective is to get an overhead product containing 97 mole percent heptane and a bottom product containing 99 mole percent ethyl benzene. A reflux ratio of 2.5 is to be used. Find out the following: the molar flow rates of top and bottom products, the number of equilibrium stages, the minimum reflux ratio, and the minimum number of stages. So in this case, you have a fractionating column, and feed to the fractionating column is a saturated solution of heptane and ethyl benzene. That means nature of the feed is given to us. The feed is a saturated solution or a liquid solution at its bubble point. It is containing 42 mole percent heptane, that is composition of the feed is given to us. The molar flow rate of the feed is also given. The feed is admitted at a rate of 630 kilomole per hour. And the objective is to get an overhead product containing 97 mole percent heptane. That means the composition of the overhead product or the distillate, it is given to us. And a bottom product containing 99 mole percent ethyl benzene. The composition of the bottom product is also given to us. The reflux ratio that is to be used, that is given. A reflux ratio of 2.5 is to be used. So based on this information, we are supposed to find out the molar flow rates of top and bottom products, the number of equilibrium stages required in the operation, the minimum reflux ratio, and the minimum number of stages that would be required in this case. Okay, so that is the numerical statement. Along with this, additional information is also provided. The VLE data for the system, the VLE data for the binary mixture of heptane and ethyl benzene, it is given to us. So X and Y values that are in equilibrium with each other, they are given to us. X is mole fraction of heptane in the liquid phase, and Y is mole fraction of heptane in the vapor phase. Why heptane? Because heptane is the more volatile component in this case. So, if you have understood the statement, you must have noticed that we are supposed to get a top product that is containing 97% of heptane. that is the top product, the maximum or the major component in top product is heptane, and this is only possible when it is more volatile. Or if it is volatile, then ethyl benzene, the other component. So X is mole fraction of heptane in the liquid phase, Y is mole fraction of heptane in the vapor phase. And these values are provided to us, X and Y values, they are provided to us, and we are going to use this in our solution. To begin with, let us first list the data that is given to us. So you have two components. Which are these two components? Heptane and ethyl benzene. The components involved are heptane and ethyl benzene. Then the more volatile component. Since the major component in distillate is heptane, as I said earlier, it is the more volatile component. Then what information about the feed is given to us? Feed is a solution of heptane and ethyl benzene. Heptane, let us denote it as A because it is the more volatile component, and ethyl benzene, let us denote it by B. It is up to you. I am calling heptane as component A and ethyl benzene as component B. Then it is a saturated solution, that is solution at its bubble point. That means the value of Q, the value of parameter Q that we are supposed to use is 1. Because for saturated solution, Q has a value of 1. Then molar flow rate of the feed is given to us. We denote that by F. So F is 630 kilomole per hour. That is given to us. Then composition of the feed is given. The feed is containing 42% mole of A and 58% mole of B. So if it is 42% mole of A, the rest, that is 58% mole, will be of B. And this composition is given on percent mole basis, and you can convert that to mole fractions by simply dividing with 100. So therefore XF will be 42 divided by 100, which comes out to be 0.42. So you must remember, if you are converting percentage mole into mole fraction, you simply divide the percentage value with 100. So in that way you get XF as 0.42. Then what information about the overhead product is given to us? Overhead product is nothing but distillate. This is distillate. So what information is given to us regarding distillate? It is containing, let me first erase, this is distillate. So it is containing 97% mole of A and the remaining, that is 3% mole of B. That means in this case XD is 0.97, that is 97 by 100. Because XF is mole fraction of more volatile component in the feed. More volatile component is heptane. So that's why XF is 0.42. Similarly, XD is mole fraction of more volatile component in the distillate. And in this case, it is 97% mole. That's why XD is equal to 0.97. Then regarding the bottom product, you have bottom product is containing 99% mole of B. That means the remaining 1% mole will be of A. The remaining 1% mole will be of A. That is why XW, that is mole fraction of more volatile component in the bottom product, it is 0.01. So this is the information that is given to us. The reflux ratio is also given. Reflux ratio, that is R. We denote that by R, and it is 2.5. VLE data is provided. We are going to use that to plot the graph and then use that graph to find the number of equilibrium stages and then the minimum reflux ratio or the minimum number of stages. So let us start what are we supposed to find? We are supposed to get the molar flow rates of overhead and bottom products, and then we are supposed to get number of equilibrium stages, the minimum reflux ratio, and then the minimum number of stages. So let us start solving the numerical. First is we will calculate D and W. So first step is calculation of D and W. What is capital D? Molar flow rate of the distillate, molar flow rate of the top product, molar flow rate of the overhead product, distillate or top product. And then what is W? This is molar flow rate of the bottom product. So first question is to find molar flow rates of distillate and bottom product. So let us do that. So for that we are going to use steady state total material balance for the entire operation, and that is F is equal to D plus W. I have discussed about material balance for a typical distillation column in my earlier videos. You please watch those videos. So for now I am going to use the expression for steady state total material balance, that is F is equal to D plus W. So F is given to us, it is 630 kilomole per hour. So if I use this in the equation, I will get 630 is equal to D plus W, and I am calling it as equation number 1. Then I will be writing steady state material balance for A, steady state material balance for the more volatile component. So it will be F into XF, that is total into fraction, F into XF, that is equal to D into XD plus W into XW. XF is given to us, it is 0.42, XD is given to us, it is 0.97, XW is given to us, it is 0.01. So therefore the equation will be 630 into 0.42, that is equal to D into 0.97 plus W into 0.01. And 630 into 0.42 is 264.6. 2464.6, that is equal to 0.97 D plus 0.01 W. That is 0.97 D plus 0.01 W is equal to 264.6. I have just rearranged the equation, and now I am calling that equation as equation number 2. So you have equation number 1, you have equation number 2. There are two equations and there are two unknowns. Which are these unknowns? D and W. So these two equations, they can be solved simultaneously to get the values of unknowns. So for that, what I will do, from equation number 1, I will write equation for W. So from equation 1, W will be 630 minus D. And now I am going to use this in equation number 2. So wherever there is W, I am going to replace it with 630 minus D. So that will be 0.97 D plus 0.01 into 630 minus D, that is equal to 264.6. Further simplification, you have 0.97 D plus 6.3, 0.01 into 630 is 6.3 minus 0.01 D, that is equal to 264.3. That is 0.97 D minus 0.01 D, that is equal to 264.6 minus 6.3. So I have taken 6.3 to the other side, and I am getting this equation. So this will be 0.96 D, that is equal to 258.3. After simplification, 0.97 D minus 0.01 D is 0.96 D, and 264.6 minus 6.3 is 258.3. That means D is 258.3 divided by 0.96. That is D is 269.06 kilomole per hour. 258.3 divided by 0.96, it is 269.06 kilomole per hour. So in this way we get D. Then we are going to use this D in the equation for W. So in that way W will be 630 minus 269.06, and W comes out to be 360.94 kilomole per hour. So in this way, step number 1 is completed. At the end of this step, we have got the values of D, that is the molar flow rate of the overhead product, or the distillate or the top product and molar flow rate of the bottom product. Now let us go to the next. Next step is VLE data is directly provided to us. So we are going to plot it. So this is the VLE data that is provided to us. So what is our task? We are going to get the distribution diagram by plotting this. And for getting distribution diagram, we are going to plot X on the X axis and Y is plotted on the Y axis. So if you do that, if you plot X on the X axis and Y on the Y axis, on X axis the scale is 1 centimeter is equal to 0.1, and on the Y axis also the scale is 1 centimeter is equal to 0.1. For reference, I am drawing the diagonal line, and when the data is plotted, you'll be getting the points will be looking like this. And after you draw the curve passing through, after you draw a curve passing through the points, the curve is the equilibrium curve. So this is the distribution diagram, and we are going to use this to find the number of equilibrium stages and then the minimum reflux ratio and also the minimum number of stages. So let us first plot the rectifying section line. So for plotting rectifying section line, we are going to use the value of XD. XD is 0.97. We are going to locate over here. So it is 0.97 XD. And then from this, we are going to go to the diagonal line. The rectifying section line is going to start at this point. Then the other information that is required is intercept made by the rectifying section line on the y-axis. Intercept is to be calculated by using this formula. It is XD upon R plus 1. XD is known 0.97, R is given to us 2.5. So intercept is 0.97 upon 2.5 plus 1. That gives us intercept as 0.28. Now we are going to locate that. So 0.28 will be coming over here. And the rectifying section line will start at this point and it will end at this point. So that will be the rectifying section line. So after plotting the distribution diagram by using the equilibrium data that is given to us, we have plotted the rectifying section line. We have to plot the Q line. For that, we need information regarding the feed. And feed is a saturated solution, saturated liquid solution. For saturated liquid solution, Q is equal to 1. Therefore, slope of the Q line, which is given by this formula, Q upon Q minus 1. Again, I have discussed about the Q line in one of my earlier videos on McCabe Thiele method. So you please watch that video. So slope is equal to Q upon Q minus 1. That is slope is equal to 1 upon 1 minus 1. That is slope is equal to 1 upon 0, which is infinite. And a line whose slope is infinite is a vertical line, because slope of a line is tan of the angle made by it with the horizontal. And if theta is 90, that is the line is vertical. If theta is 90, then the slope will be infinite. So that's why in this case the Q line will be simply a vertical line and it will be starting at XF. X is equal to XF on the diagonal line. So we need to locate XF for that. So XF is given to us, it is 0.42. So I will locate 0.42 XF over here. This is 0.42. And from this point I will be going to the diagonal line, and now I know the Q line is going to start at this point, but in this case it is simply a vertical line because its slope is infinite. So you get the Q line. So after plotting the Q line, you are getting the intersection of rectifying section line and the Q line. So the next line, stripping section line, is going to pass through this intersection, and we are going to use that information for plotting the stripping section line. Okay, now let us plot the stripping section line. For plotting stripping section line, what information is required? XW. XW is given to us, it is 0.01. So let us locate it. So it will be located at this point, XW 0.01. So the stripping section line is going to start at this point and it will be passing through the intersection point of Q line and rectifying section line. So this will be the stripping section line. Okay. So now the basic structure that we are going to use for finding the number of equilibrium stages, it is ready. Now you just have to drop the stages. So for that, we will be starting at this point, XD, the point at which the rectifying section starts on the diagonal. So I will be traveling a horizontal distance till I reach the equilibrium curve, then a vertical distance till I reach the rectifying section line, then horizontal. I'll be traveling horizontally to reach the equilibrium curve, vertically to reach the rectifying section line, then to equilibrium curve, rectifying section line, equilibrium curve, rectifying section line, equilibrium curve, rectifying section line, equilibrium curve. Now, if I travel in the vertical direction now, I would have crossed the intersection of the three lines, that is rectifying section line, stripping section line and Q line. This means that I have crossed the feed stage. That is, I have completed my travel in the rectifying section. Now I will be traveling in the stripping section. So how to do that on this diagram? So after going horizontally to the equilibrium curve, now this time I will be coming to the stripping section line, since I am now in the stripping section. So again, horizontally to the equilibrium curve, to the stripping section line, to the equilibrium curve, to the stripping section line, to the equilibrium curve, to the stripping section line, to the equilibrium curve, to the stripping section line, to the equilibrium curve and to the stripping section line. So when I do this for the last time, I have reached XW, that is 0.01. Then I have to stop drawing those stages. Now what task is left? We have to count the number of triangles that we have drawn in this process, and the number of triangles in this case will be the number of equilibrium stages. So let us count. This is 1, this is 1, this is 2, this is 3, this is 4, this is 5, and I'll use a different color to indicate that a 6th stage is the feed stage. Why it is a feed stage? Because on this triangle you have the intersection of the three lines, the rectifying section line, stripping section line and the Q line. Then when you are in the stripping section, I will use a different color. So 7th plate will be in the stripping section, 8, 9, 10, and there is one small, that is 11th stage. This is actually the reboiler. So in this case, number of stages is Ni is 10 plus 1 reboiler. There are 10 stages and 11th is the reboiler. So number of ideal stages is 10 plus 1 reboiler. How many stages are there in the rectifying section? Stages marked with red color. So there are 5 stages. Which one is the how many stages are there in the stripping section? Stages marked with blue color. So 1, 2, 3, 4 and 5. The reboiler is also in stripping section. And which is the feed plate? The stage marked with green color. 6th plate is the feed plate. So in this way, there are 11 number of stages. Out of those 11 number, one is out of those 11 stages, one is the reboiler. There are 5 stages in the rectifying section. There are 5 stages in the stripping section, and 6th stage is the feed plate. So in this way, you have to the number of equilibrium stages. Now, the second task, first question was to get the molar flow rates, D and W. We got them. Then the second question was to get the number of ideal stages. We just got them. Now, the third question is we are supposed to get the minimum reflux ratio. So for that, I'm going to use the diagram that was used previously for finding the number of stages. You can do this on the same graph over here so that you will understand, so that you can understand I'm using a separate, I'm showing it separately. So for finding minimum reflux ratio, I am interested in this point. What is this point? This is the point where the Q line intersects the equilibrium curve. So that point, I will note the y coordinate of that point. It is 0.68, and x coordinate of course will be 0.42 because since the Q line is vertical line, x coordinate of this point will be same as x, that is 0.42. So if I call this point as m, and the coordinates of this point are x star and y star. Again, I am giving link to my video where I have discussed minimum reflux ratio. You'll understand. If you watch that video, you'll understand the concept. So for now, I'm calling this as point m, and let the coordinates of this point be x star and y star. X star is 0.42 and y star is 0.68. So x star is 0.42, y star is 0.68, and then minimum reflux ratio can be found out by using this formula. Again, I have derived it in my discussion on minimum reflux ratio. Link is there in the description section. You please watch that. So our minimum is given as xd minus y star divided by y star minus x star. So y star x star, we just got xd is 0.97 minus y star is 0.68. Y star is 0.68 and x star is 0.42. So that gives us the minimum reflux ratio as 1.12. The minimum reflux ratio in this case is 1.12. So that is answer to the third question in this numeric. Now now the fourth question is we are supposed to find minimum stages, minimum number of stages, which will be the case when the column is operating under total reflux. For that, again, we will have to use the same graph. You can do all the 3 tasks: number of ideal stages, minimum reflux ratio, and minimum number of stages on the same graph. But in my discussion, I'm showing them separately so that you can understand. So for finding minimum number of stages, we are going to use this. You have to use the same graph. And the minimum number of stages will be drawn between the equilibrium curve and the diagonal line. So if you have to find minimum number of stages, the stages will be drawn between the equilibrium curve and the diagonal line. So you start at this point, xd, go to the equilibrium curve, come down to the diagonal line, go to the equilibrium curve, come down to the diagonal line, go to the equilibrium curve, come down to the diagonal line, go to the equilibrium curve, come down to the diagonal line, go to the equilibrium curve, come down to the diagonal line, go to the equilibrium curve, come down to the diagonal line, go to the equilibrium curve, and finally you come down to the diagonal line, because I'm saying finally because you are crossing this point 0.01 xw. Okay, so in this way you can draw minimum number of stages. You cannot draw lesser number of stages, lesser than what I have drawn now. So let us count the stages. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and the last one is 7th stage, which is the reboiler. So in this case, number of stages, minimum number of stages is 7. So that is 6 plus 1 reboiler. Here there is no question of feed plate, because when the column is operating under total reflux, feed is not continuously admitted to the column. Initially enough feed is given to the column and then it is stopped, and then the column is operated under total reflux. Again, my discussion, I am giving link to the video in which I have discussed the concept of distillation under total reflux. You please watch that. So the answer to the fourth question, there are 7 stages. You cannot have less than 7 stages. So the minimum number of stages in this case is 7, 6 stages and 1 reboiler. So with this, I end my discussion on this particular numerical. Here, you must have learned how to find out the minimum reflux ratio and also how to find out the minimum number of stages. I hope you have understood the numerical, you have understood the solution. If you have any doubts, you please mention them in the comment section. And you please watch the related videos. I am giving links to those related videos in the description section. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day and hope to see you soon in my next video. Thank you. Have a nice day. Bye bye.